All right, so let's pick up where we left off last time. We were. Shut up! Pick up where we left off last time. We were talking about the difference between Java and C Sharp. We talked about Java Virtual Machine and how that can kind of create a slowdown, right? Because you have this translator that's sitting between your program and the computer itself, the hardware, and making all those translations so things slow down. Talked about at the high level, Microsoft stealing Java, them getting sued, blah, 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 coming out with C Sharp. C Sharp is largely identical to Java, but they did make some improvements, let's say, where they still said it's platform independent as long as you're running Windows. Really, it's as long as you're using the .NET component architecture, which is actually coming to Mac soon. But it does use something called a just-in-time compiler the very first time you run the application so that your application becomes native code on the CPU. Let's kind of review what that means to be native code on the CPU. It's really something at the core of programming. When we talk about the CPU, remind me, what does the CPU do in our computers? How would you describe the CPU? Go ahead. Okay, so it's a okay. I like that collection of magic tricks. So our CPU knows how to perform all these different magic tricks that each one accomplishes something very small. Okay, so it has this big list of magic tricks it knows how to do, of tasks that it knows how to do, and then when we write our programs, one way or another, we ultimately need to get down to the level where we're telling the CPU, perform this magic trick, then this magic trick, then this magic trick, and eventually something real has happened because you've called enough magic tricks in a row that happen to be, this guy talks to this guy, which talks to this guy, which talks to this guy, and then you've actually accomplished something. Now, the issue is if you're a company like Intel or AMD and you're designing processors, you're designing guys for performing these magic tricks, and then you have the kind of the core list of magic tricks that already exist if you want your processor to be backwards compatible. So for example, if AMD comes out with a brand new processor next week, as consumers, we expect to be able to install Windows on that processor, right? So that means that processor at least needs to be able to support all the magic tricks that processors that can run Windows can support. They can add some new magic tricks for people that want to specifically take advantage of something on the AMD processor. But in general, it has to be backwards compatible with older processors, which means that list of magic tricks needs to include all the magic tricks that Windows tries to call. Right? When somebody wrote Windows and and they compiled that code, so somebody wrote Windows probably in a high-level language like C++, and then that code compiles down to, I asked last time, what does a compiler do? And I think he mentioned that a compiler translates from a high-level language to a low-level language. Okay, remind me, what's the difference between a high-level language and a low-level language? Go ahead.
High-level language is more English-like in its kind of structure.
Okay, that's true. There's a deeper core difference between them, but that's accurate. Tell me more about the difference. We prefer high-level languages, right? High-level languages are kind of a power tool. So I typically say that a high-level language has a one-to-many relationship with the CPU. We write one line of code in a high-level language like C++, like Java, like C Sharp, and it translates into a whole bunch of those magic tricks that the CPU knows how to process. Okay? Whereas if we were writing in a low-level language, like assembly language, it's a one-to-one relationship. If we want to call this magic trick, we write this line of code. We want to call this magic trick, we write this line of code, so on and so forth. All right? So the way a CPU indexes its magic tricks is in binary, because zeros and ones is what computers like. So, instead of us saying, I want to move something from this memory location to this memory location, which is what we might write in an assembly language. So we might say move AX, BX. That would be an assembly language instruction where I want to move the contents of this memory register into the contents of this memory register for some reason. That's going to translate into a magic trick on the CPU that might be something like that. Okay, where maybe this is the memory address of BX, this is the memory address of AX, and then this is the index of that magic trick. Something like that. Okay, so as human beings, we're not huge fans of just tapping out zeros and ones. So we don't want that 2-button keyboard. Okay, but this is palatable for us. That's readable for us, right? So with an assembler, if we write a code in assembly language, which is a one-to-one relationship, the assembler will translate the code I have highlighted there into the crazy stuff. So it does us a favor by doing that, but it's still a one-to-one relationship. This is a single magic trick that we're asking the CPU to do. So you can imagine as a computer programmer writing assembly code, that would be a very tedious job, right? Because we are talking to the CPU as if we're on a one-to-one basis. We have this giant list of magic tricks the CPU knows how to do, and to be honest, not one of them is all that interesting. But if you use them in the right order next to each other, you can actually accomplish something real. Okay, because a lot of those magic tricks happen to be like system calls back to the operating system and stuff like that. Like, oh, I want to print something to the screen. Well, I got to load some stuff here. 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 Because those are all the places that when I tell the operating system to print something, it's going to go and look in those places to find out what I want to print. So I got to load everything up. Then I got to say, hey, operating system, go and print stuff. And it will go and look in all those memory locations that I loaded up and go and actually print the stuff and then give the control back to me, and I keep going. Okay, so you can imagine if you're writing an operating system, it becomes even harder because the people who wrote Windows, the people who wrote Linux or Mac OS, they had to implement that write stuff to the screen. So they had to tell your graphics card how to spit text out to the monitor. So this is where we get hardware drivers, the pieces of software that drive your graphics card or that drive your USB mouse or something like that. So we have all these different little layers of software that lives around our computer. And depending on which layer we're writing stuff for, you might be a software driver writer. Where you work for NVIDIA, you work for AMD, and you're writing software to control the latest, greatest graphics cards. Because a graphics card isn't necessarily any different than what we're talking about with the CPUs. A graphics card has this big list of magic tricks that it knows how to do, and when new graphics cards come out, they have more magic tricks on them to make them better, more powerful, blah, 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 than the previous good card. But they still have to have a subset. They have to have the magic tricks that graphics cards have had for a long time. So a graphics card either needs to be OpenGL compliant or DirectX compliant, where those effectively say, here's a list of magic tricks that you must support if you're going to support DirectX. Because these are things that all games, for example, written in DirectX will expect that they can tell the GPU to do, the graphics card to do. But then you can have a game that takes advantage of maybe the latest, greatest bells and whistles that the latest NVIDIA card came out with that might be something that's beyond what's just defined inside of DirectX. It's something extra. So if you have that card and you have a game that happens to take advantage of that feature of that card, then it'll make these extra calls to make things faster. Okay? But it's the same model as we deal with CPUs. And we have a brain that knows how to perform a bunch of magic tricks, and you just give it instructions. Jump, smile, wave, one step forward, one step back. That's what we're doing with our CPUs. All right, but to avoid writing stuff in zeros and ones, human beings at least need to have something that's more English-like. Okay, but as he pointed out, with a high-level language, we like something even more English-like. Rather than writing 20 lines of assembly code to print something to the screen, we'd rather just say, print hello world, and move on with life. That's friendly for us. And why should we have to do the heavy lifting when we have machines to do it for us? Okay, so CPU, collection of magic tricks, and when we have a low-level language, we're talking to that CPU on a one-to-one basis. A high-level language, we're talking to the CPU on a one-to-many basis. So we write one line of code in a language like Java. It's going to translate into a whole bunch of stuff on the CPU. And we rely on the Java compiler to explode out our high-level code in Java into the zillions of lines of assembly code that's equivalent to it. Realistically, though, it's a zillion lines of code of Java bytecode that the Java virtual machine knows how to handle, which then translates those things on a one-to-one basis to the magic tricks that the CPU knows. Make sense? So we have all these different layers. All right, so programming lives in all sorts of little spots inside of our computers, and as human beings, we like working with power tools, right? You'd rather use the power drill for screwing stuff in than the little manual screwdriver, except when you're doing little dainty things like screwing on the faceplate to a light switch. Don't use a power drill to do that. You will crack the plastic faceplate. All right, so CPU, collection of magic tricks. This is ultimately the dude who's going to do the work for us on our computer. This is the guy we're talking to. Okay, when we write our code, we're talking to this guy and having him take over. Okay? We might say we're talking to this guy along with the operating system. Those two guys together, something that you'll learn when you take the 350 class, the operating systems class, is you'll deal with just the generic definition of an operating system, that it's this piece of software that sits between the end user and the hardware. Because we're not going to be sitting here, delivering little electrical signals to the actual motherboard of our computer. Sitting here with a soldering iron and stuff like that, and jumping wires and that kind of stuff. That's not the way we use computers today. We like using keyboards and mice and double clicking on stuff. So we need a friendly piece of software that lives between us and that hardware to accomplish that. All right, and somebody had to write that software. And that software is, on a first name basis with the CPU to accomplish things. Okay. So really, when we're talking about platform independence of Java and C#, we're really talking about how does it ultimately get its instructions to the CPU. Okay? So Java gets its instructions to the CPU by having its bytecode translated in real time into native assembly language or native instructions for that CPU using the Java virtual machine. C#, the very first time you run the program, your Microsoft Intermediate language, the missile code, gets translated into native code for that CPU, but only that very first time. So from that point forward, when you run your application, it's a native application running directly on the CPU. So it's getting that speed, but it relies on that .NET component architecture to do that translation the very first time. Okay. Now Java has learned some of those tricks, and they've introduced some JIT compilers into the Java framework for pulling off the same thing, but it doesn't do it in its entirety. So there are some performance benefits of Java today versus call it 15 years ago, but it's not quite where it needs to be, and most of that is probably because it's lost that race. Java is not going to be used for creating games or high performance applications anytime soon. It's not what it's made for. Okay, but Java is great for business applications. So you can write Microsoft Word, for example, for both platforms. Okay, technically Microsoft Word is written in C# now, but the point is that if they were starting from scratch today, they might choose Java if they weren't Microsoft. There's a little bit of an issue when you deal with these big companies. If you were Microsoft, would you want your software to be reliant on another company's product? So, even though Oracle isn't a direct competitor with Microsoft, Oracle's the current people who they bought Sun Microsystems years ago, so they're the ones who currently own Java. If you're Microsoft, even though technology-wise it might make sense to write your software in Java so it's cross-platform, so it's on both Windows and Mac and Linux and all that stuff. From a business perspective, it doesn't make sense for one of your flagship products to be reliant on technology from a competitor. They are a competitor because Microsoft makes SQL Server, which is a database, and that's a direct competitor with Oracle's database server. Wouldn't make a lot of sense, even though from a technology perspective it might. Okay? So Microsoft, writes Microsoft Word twice. They write a Mac version and they write a Windows version. And now Microsoft is starting to port their .NET component architecture over to the Mac, and they actually have a Visual Studio product now for the Mac, so you can write C# code over on the Mac side of things. Okay, so let's start getting into well, here, we'll just reproduce these slides. How do humans solve problems? So we use our memory, we ask questions, and repetition. Okay? And we had a slide called the mapping. Memory is accomplished through variables. Asking questions is accomplished through conditionals, usually if statements. Condition. And then repetition is called loops, functions, that kind of stuff. All right. So if I'm saying human beings solve problems using their memory, asking questions, and repetition, and I'm also saying that 100% of programming languages have facilities for those three things. Some languages then have some extra stuff bolted on that maybe lends themselves to certain kinds of problems. So for example, like the language PHP was a language originally designed for doing web stuff. So it has some extra stuff built into the language that make things that are commonly done for web pages more convenient. But it still has facilities for variables, for conditionals, and for loops and functions. Okay, so every single programming language you ever learn will have these facilities. So now, as far as I know, since all of you have either had credit for 200 or whatever, you've had some programming background, but for those of you who had 200 last semester, you currently have been exposed to Python, right? So in Python, you know how to declare variables. You know how to ask questions. You know how to write loops and functions. Okay? So if you're going to learn Java, the first step would be, how do I convert my current knowledge of programming in Python into what's the equivalent syntax for creating variables, for asking questions, for loops and functions in Java? And then all of a sudden, we can solve a large classification of problems in this language that we haven't necessarily been exposed to, just leveraging the fact that we are, let's call ourselves intermediate programmers. Okay, we know enough to be dangerous in Python or whatever language you've had before. And now we're going to translate that over to the Java world. Programming is programming. We're not going to have to change the way we solve problems. We're just going to change the words we're using, and not even that much. Okay? Now, one thing we do have to deal with when we make that jump from Python to Java back to this slide about two kinds of programming languages. We have loosely typed and strongly typed. Anybody remember what the difference between a loosely typed language and a strongly typed language is? Okay, so don't have to define, well, let's just say it out loud because I want to be more generic with this. So in a loosely typed language, when we create a space for memory, we create a bucket for holding it to remember something, mimicking our memory, we don't have to define the kind of value we'll be holding in there. That's what a variable type is. So I think the example I usually use is something like if you go to Target and you buy a piece of Tupperware, to put under the bed, and you decide you want to keep tax documents in there or something like that, and then 6 months later, you decide, screw the government, and now you're going to keep shoes in there. You don't have to go buy new Tupperware. As long as the shoes will fit in the container you previously bought, it wasn't earmarked for only being capable of storing a certain type of value, right? You could store tax documents in it. You could store shoes in it. No problem. So loosely typed languages allow you to create named containers without defining the kind of value that it's capable of holding. So you can put whatever you want in there. In a strongly typed language, when you went to Target and you bought that Tupperware, the day you bought it, if you were going to store tax documents in it, you put a little piece of masking tape on the front of it that said tax documents. Okay? Now I'm going to tell you that this masking tape is permanent masking tape. Okay, it doesn't come off. So if you then decide, okay, well, I'm no longer going to keep these tax documents and I want to put shoes in there, you're not going to be able to fit your shoes in the bucket. You're going to try to throw them in there, it's going to spit them back out because that bucket was originally created and it was only capable of holding tax documents. If you want to hold shoes now, you have to go back to Target and get another container for holding shoes. That makes sense? So strongly typed languages, when we define a variable, we have to say what kind of value we're going to hold in that variable. Loosely typed languages, we don't. What kind of language was Python? Loosely typed. So when we wanted a variable in Python, we just said a equals 5. No problem. And if we, 2 minutes later, we wanted to say a equals hello, that's fine as well, right? We can put whatever we want in that bucket. Now, realistically speaking, in terms of how you typically write code as a programmer, you're probably going to stay consistent. If you create a variable called my age, and you're going to hold your current age in there, chances are, because of your intention of that variable, you're probably always going to put a number in there, right? But the point is, in a loosely typed language, you don't have to. It doesn't have to be a number. Now, the flip side, if you're in a language like Java, which is a strongly typed language, if you're going to define a variable to hold an age, and you want it to be a number, you have to mark it. When you create it, you have to say, here is a variable named my age, and it's capable of holding integers. And from that point forward, you can only put integers in there. It will scream at you if you try to put anything else. Which is better, loosely typed or strongly typed?
Yes.
Okay, explain.
Well, they're both good for different situations. Loosely typed is good for kind of writing something quickly, whereas strongly typed is a bit more if you want something stable and secure.
Okay. Without getting into it too far, this actually could be an interesting debate. What I'm very interested in is how does a loosely typed language actually allow you to write it more quickly? Most loosely typed languages make you say like the word var. Var a equals 5. Where in Java, it's int a equals 5. It's not any faster. Go ahead.
I think strongly typed better because the loosely typed rely on the type implementation, so it's slower.
So we do have a performance difference. So a loosely typed language like Python, because we don't necessarily know what kind of value is living in there, we have to have a type inference engine. We have to have this guy that floats above there and kind of peeks in the box before it lets you use the value to make sure if you're trying to do like some addition, that you have something inside the box that's mathable that you can do math with. So you do give up performance with a loosely typed language. Okay, I agree with that. Where I have issues is what's the real advantage of a loosely typed language? I don't think it's speed, because I don't think it's any faster to write, define a variable in a loosely typed language than it is in a strongly typed language, because most loosely typed languages are requiring you to put the word var or something like that in front of it. Or in the worst case, it's one little tiny word. And as I just explained a few minutes ago, when you're a programmer, you're applying a proficiency in programming as a skill set, typically when you define a variable, you have in your mind what you're going to store in that variable, right? It's not like you're going to use this variable and it's going to be this all-terrain vehicle where 1 minute it's holding numbers, another minute it's holding strings, another minute it's holding ice cream cones. Okay, even though it's possible in a loosely typed language, that's not something that's really a common occurrence. It would really be bad programming practice for you to, because typically when you create a variable, you want a variable to have a meaningful name. A name that kind of indicates the kind of value we're going to put in there. So if you have a variable called my age, and later on you find out that somebody stuck an ice cream cone in there, that's going to be surprising. Okay, so it's probably not real practical, even though technically it's possible. Now, the best argument you could probably make for loosely typed languages versus strongly typed languages in terms of the trade-off, because as you said, A loosely typed language will be slower because you have this extra oversight that has to occur. Now we have to look at it from the side of things of if you're creating the language. So like in this semester in the 470 class, it's programming language theory, we are writing a programming language. We're creating a language from scratch. So if you're the person who's writing a language, who's implementing the language itself, implementing a loosely typed language is more simple, is simpler than implementing a strongly typed language. So now you might have situations where maybe performance isn't the most important thing because, our computers are pretty fast today. So even though we can say that, Python is tactically slower than Java, let's call it 99% of all applications we write, we're not going to notice because our computers are way faster than we can tell. Right? So that translation step, no big deal. Okay, we're not gonna see it. Games and stuff like that, you would see it at that level, but for most business applications, it's going to be meaningless. So as I mentioned a little bit ago, several programming languages are built for very specific purposes. Okay, so even though all languages will have facilities for memory and asking questions and repetition, certain languages were put together to kind of easily solve a very specific kind of problem. As I mentioned, PHP kind of focused on web development stuff. Not that you couldn't solve other problems with it, but you probably wouldn't use it to solve other problems because there's likely languages that are, more bent towards those kinds of problems. So with that in mind, it might allow folks to create languages for solving problems within a certain kind of field, certain genre. It might make it easier for them to define those languages if they are loosely typed languages because the way you would write the interpreter for those languages is easier than writing a compiler for a programming language. That makes some sense? Now, for most of us, that's not our problem. Somebody else wrote the language. I don't care how hard it was for we're the users, okay? But if you do get into the industry and you decide that I'm going to be a language writer, which is my background, well, then you might care. So it's kind of that type of thing. So at the end of the day, we want to understand the difference between loosely typed and strongly typed languages. That there are side effects. Loosely typed are lower performance, strongly typed are higher performance. So if we were at work and somebody asked us to solve a problem, and the very first question we might ask ourselves is, well, is performance an issue here? Is the problem I'm trying to solve, does it require a high performance solution? Or will any computer be able to pretty much just handle this? If any computer can handle this, we would have both loosely and strongly typed languages would be on the table. If it needed to be high performance, we'd probably throw loosely typed right off the table and just say, let's focus on strongly typed languages and choose from there. Yeah.
What do you mean by lower and higher performance?
So let's say that we're doing the best example would be like in video games. So something that needs to have a very high frame rate, needs to run fast. The end user has this expectation of things going very quickly. If you want to take it away from video games, you might say it's something like in the medical field, maybe simulations or something like that, when they're doing chemistry or biology simulations. It could be the difference between a simulation taking an hour to run versus something taking a day to run. Depending on the language you use, because it's doing a lot of mathy calculation stuff, and just the amount of stuff it's doing would benefit from a strongly typed language just from a performance perspective, because now that's turned into real time. A majority of the programs that we write, especially as students, they run instantly, right? The difference for us between a loosely typed and a strongly typed language is some fraction of a second. Not really noticeable to us. We wouldn't have been able to be productive in that period of time. But when you get into some of these problems that are reliant on that performance difference, now we might need to make that choice. That, okay, if we write this in a loosely typed language, every simulation is going to take a day. And if we need to make a tweak, we're not going to be able to make that tweak and test it again until tomorrow. Strongly typed language, we can make multiple tweaks in a single work day, something like that. All right, so one's not necessarily better or worse than the other. You want to think about the problem you're trying to solve and what's the best tool for solving that problem. Okay, which kind of then leads us into this thing that I hear a lot of computer science folks say. And I do give you permission that if anybody says this, you can just sock them. Just, probably open hand, I would say. But they'll say, well, I know C#, but I don't know Java, or I know Python, but I don't know this. So oh, you're looking for this type of developer? I can't do that. Again, I'll say it. Programming is programming. Okay? Any kind of programmer can get up to speed in a different language that they haven't been exposed to pretty quickly. Okay? Once you have computer programming as a skill set. Yeah.
Do you suppose that would also apply to changing paradigms, like going from like C++ to a functional programming language like Pascal or something?
Absolutely would. Because you're going to still have, because that's not a complete change in paradigm. You're still going to have the ways of defining variables, asking questions, repetition. The difference you probably run into in most functional languages is you have to start thinking more recursively, and you also are working with a smaller tool set. So if you want to think about it, in like a real life example, let's say that you're having a castle building contest with Legos. All right, and you got two people here. One person has the giant deluxe set of Legos where you have a zillion different shapes Legos, and you have options. We're over here, so that's the C# guy. Okay, he's got a zillion options on how he can build his castle. Now the Haskell guy or the Scheme guy, the Lisp guy, these functional languages you're referencing, he's got this, the starter kit. Okay, starter kit Legos, where he's pretty limited on what Legos he had. Now that doesn't mean he's going to lose. Okay, that doesn't mean he can't build a pretty cool castle, but he's got to solve that problem in terms of the tools that are available to him. So kind of that idea. There's a right tool for the job. Maybe there's almost too much stuff here. Maybe this guy's not going to be efficient at building this castle because he's going to spend half his time looking at deciding what's the right color Lego to use for this. Where this guy just has a bunch of yellow Legos. So I'm going to have a yellow castle. That's what it's going to come down to. But there is probably going to be some truth to what you're saying. I think what you're referencing when you're saying paradigm shift is just that change in way of thinking. So even though you have all those core concepts, we're going to see it in the game programming class this semester. For those of you who are taking the 275 class, even though you've had programming before, so the C# scripting stuff we'll do in Unity is not going to be a huge leap for you. Syntax will be a little different. If you're in this class, you'll see that Java and C# are very similar. So it's not going to be a giant leap. But you will have this new learning curve of learning the Unity software and then kind of working with, dragging stuff around and rotations and, using a tool set that really isn't a programming tool set as much as it is a design tool, right? For getting stuff on the screen and making it look less offensive. I'm not going to say make it look good because most of the stuff we write will not look good, but it'll look okay at best. So there will be that learning curve, but that's not really even the programming aspect of it as much as it is just the imagination design aspect. What we've done so far and what we'll do for the first half of this class is all of our stuff is still going to kind of live in our imagination. Last semester we did like the soccer team application where we had a player object. Well, what was a player object? Well, it was a guy. Okay, but it was all imaginary, right? He had like a skill set, he had a first name, I don't remember if he had a last name, whatever. He had some attributes associated with him, but it was all in our imagination. Where if you're going to write a game in Unity, well, you might actually have a player. You put this little Mario dude out there on the screen or something like that, and that's my player. Now, behind the scenes, you might create the player object and say, I'm going to attach this to that guy because he's just a picture. Behind the scenes, he's going to have this data structure associated with him that remembers his name, his current health, and that kind of stuff. But it is when you're taking a tool like Unity for game programming, you are adding that additional layer of something you didn't necessarily have to deal with as a generic programmer. We're going to see it in the second half of this class when we start doing Android stuff, or we're going to have visual stuff on our screen. We're going to have a button, and when you click that button, stuff happens. So we're going to have a physical movement here where we're actually touching the interface, and then we're going to have some code that gets called behind the scenes as a response to that event. All right, so then things become a little bit more visual. So a learning curve we're going to have is the the interface building aspect of an Android application. We're already going to be relatively comfortable with the Java stuff. We'll kind of have to learn about some of the new kind of built-in functions that are in Android. These are, you want to write the stuff that when the screen first launches, you put that stuff here. All the logic that you want to have occur, you put your Java code here for that. But now we're going to have this whole new side where we have to have our interface instead of what we would have done last semester where we, sometimes we put like, a line to separate stuff and we just print crap out the screen to show us our output. So we're changing the way our interface works. So you do have that when you go from tool to tool. But then even within that, when you have your different genres, so like in the game programming class, we're looking at Unity versus Unreal Engine right now. Well, we're choosing Unity in the class, but if you're an expert in Unity and you need to go over to Unreal Engine, the learning curve will be small. You pretty much already know the kind of stuff you're going to be working at. Their graphical editor is similar. It's not going to be a huge jump. I think the same thing's true for us in here. So the punchline of all of this is, again, in this class, like I kind of focused on the last class, focus on the programming skill set. Don't worry about that we're using Java, okay? If anything, you can just think that we're using a language that happens to be an example of a strongly typed language, so it's going to have that little tiny paradigm shift. And it really is a tiny paradigm shift because, as we said before, in languages like Python that were loosely typed, we still pretty much treated our variables as strongly typed. When we created a variable, we really only had in mind that we were going to put one kind of value in there. We just didn't have to do that. So really our problem-solving paradigm really hasn't shifted. Other than Java is going to 100% say, look, you didn't tell me what kind of value you want to put in here. I'm not going to let this compile until you do. So Java is just going to require that. Okay? So loosely typed, lower performance, but so what? Strongly typed, higher performance, so what? Every now and then that so what might turn into, that's important. So just like anything in real life, use the right tool for the job, and sometimes there might be multiple right tools for a job. If you are writing a native program for Windows for work, and let's say performance is a thing, and it's a graphical Windows application. Well, your choices might be, we'll just keep it simple and say your choices are going to be C# and C++, especially if it's a graphical application, because you would probably use Visual Studio, which has a drag and drop interface for making your business application, your buttons and that stuff. Well, so choosing between the C++ code behind and the C# code behind, because your interface builder is going to be the same. You're using Visual Studio's a tool for making your interface with text boxes and buttons and that stuff. And then you're just choosing what language behind the scenes am I going to use. Do I type my logic in C++ or do I type my logic in C#? Well, all things being equal, you're going to choose which of the two languages you feel most comfortable with, or depending on what the business application does, maybe which one has compatibility with some of the third-party libraries you might need to use for your application. Like, for example, if you're going to have Google Maps in it, there might be a decent chance that Google Maps doesn't have a real easy-to-use API for C++, but it will for C# because it's a much newer language. So then maybe that's your decision maker. I need Google Maps. C# is easy to use Google Maps with. C++ is not. So, boom, there's my answer. If all other things are equal, and they both have compatibility with the stuff you're going to use, then just pick the language you like better. If you've been exposed to C# for a bunch and you're comfortable with that language, maybe you pick that. If it's not a real high priority project and it's something that you could probably wrap a learning experience into, maybe you choose C++ because you want to kind of be exposed to it and be able to feel like you have a little more confidence with the syntax in that language. One's not better or worse than the other for the problem. Kind of makes sense what I'm getting at? Use the right tool for the job. There isn't a such thing as a best programming language. Which is a very... Huh?
Unless you're talking about C.
No, I don't think that's true. C programmers might make that argument. I had a very interesting, I was visiting, we have several of our seniors from last semester who are working at Acuity up in Sheboygan now, and several seniors from the year before as well. So I was up there visiting those guys, and one of the people in their training group is this Russian guy, and he was has an undergrad in computer science, and just he has it in his mind that there's such thing as the perfect programming language, and he's going to design it. He was very drunk. Okay, and I have fun in those conversations anyways, but given that it's my background, I'm probably the wrong person to debate on it, but it was a fun debate, and there's a right tool for the job. I mean, that's like saying that, a carpenter has his favorite hammer. It's like, well, this one is just better than the rest of the hammers. I have my favorite power drill, and we've already covered that that's not a good tool to use for screwing the little delicate plastic. Well, another thing, you see like these overhead light things, the plastic things that are quite brittle. Yeah, man, because I was getting a lot of glare on my big screen TV in my office. I have 2 lights in my office, so I wanted to unplug the lights above that. Man, I took that thing down in pieces. I ripped like 4 chunks out of it. And once you break it the first time, then it doesn't even matter at that point, right? You just kind of just rip it down. So I maybe could have gotten away with 1 crack, but it wasn't even just a little crack. I mean, I just ripped a swath out of it, like it was a bear going at it. That was not delicate, but no more glare.
There you go.
Okay, so we're good with Java as a strongly typed language. So now let's talk about variables. Because again, to get up to speed in any programming language, you're going to ask yourself, what's the syntax for creating variables? What's the syntax for writing conditionals? What's the syntax for writing loops and functions? Once I got those things under my belt, I'm most of the way there for solving general purpose problems. Then as I kind of bump into things like, oh, well, I kind of need this kind of thing. Do I have to write it myself, or is it built into the language? Something we're going to deal with near the end of this semester, and also next semester is things that are generally referred to as data structures, even though everything's kind of a data structure. And one of the things we're going to work with is something called a linked list. So we've dealt with arrays, lists of things. Now, in Python, lists were built as linked lists. So they were arbitrary in size. So we could just keep adding stuff to our lists. Well, in Java, we have a thing called an array, and it's not arbitrary in size, it's fixed. So we might say, okay, well, here's something that's capable of holding 10 things. Okay? Well, what if you don't know how many things you need to hold? What if you need to hold possibly 50 things? Or maybe it's just one thing. Well, one approach is we can just make a gigantic container that we know is going to be big enough, and if we are wasteful of space, then fine. Kind of like you get the big Tupperware for your tax documents, you just put one tax document in there, and then you realize you're too lazy to keep tax documents, so you just stop keeping them. So you get this mostly empty container under your bed. By the way, if you have cats, don't put containers under your bed. They don't have lids on them. Those are litter boxes. That's what those are. Okay, so what's this?
No, they're beds.
Well, they typically aren't beds if they first used them as a litter box. They might alternate. One container is the litter box. Put lids on them. All right, so in Java, variables, we have the type, followed by the name, then optionally equals the value with a semicolon. Okay, and typically the way you would write something that's optional is you would put little square brackets around it like this if you're formally defining the syntax for something. The stuff inside of square brackets would be an optional part of the syntax. But I'll show you 2 examples of this so you can kind of see how it's optional. Okay, so we're going to have the kind of value that this variable can hold, the name of the variable, and then the value that's going to store in there. And we end all of our statements with a semicolon in Java. And maybe instead of saying all, I should say most statements. The answer is it really is all statements, but from what you'll initially see, it'll feel like most until you understand the real nature of a statement. So for example, we can say int a is equal, it's got to be lowercase, but int a is equal to 5. All right, so I'm defining a variable named A. It's of type integer. It's going to be equal to the value 5, the integer literal 5. I could also say int B, and then later on I could say B is equal to A. Something like that. So now I defined a variable B capable of holding an integer, but I have not put an integer in there yet. Later on, I entered into B the value contained in A. And this is not a literal value, this is a variable, so that variable needs to be resolved. A holds a value, it holds a number, because we know it's a number because A was capable of holding an int. So when I resolve A, it comes down to the value that was in that. In this case, it's a 5, so this is essentially setting B equal to 5. Make sense? So that's how you define variables in Java. So then the question pops up, well, what are my options for these types? All right, so we have our built-in types, and then we have object types. So let's talk about the various choices for types in Java. We're going to call these the primitive types. All right, and we did introduce these last semester, but I introduced them as generic primitives to kind of talk about the difference of variable size. This was in our discussion when we were talking about the history of languages, C to C++, to C#, and Java. So we have something called a byte, a short, an int, a long, a char. I wonder if there's a way to just turn off the capitalization. A float, a double, and a Boolean. All right, so all of these guys are the same in C, C++, Java, C#.
Does it have a long one?
It does not in Java. Okay, so all these guys are the same in, pretty sure it does not. It does not because there's object-based for larger values. So all these guys actually came from C, and then were inherited by C++, and then were inherited by Java, and then were inherited by C#. The one guy that's changed a little bit is this dude down here. So in the old language C, Booleans, which are true-false values. A Boolean in C was actually they used int to represent a 0 or a 1, true or false. In C++, they introduced the what was called a hashtag define for bool, capital B, capital O, capital O, capital L. In Java, it's Boolean. In C#, it's bool, all lowercase. That's all the same. Just that's the difference, right? Between C# and Java. Java spells out the word Boolean for its Boolean type. C# calls it bool, B-O-O-L. All right, same thing. So now what do these guys mean? Well, a byte, and we've had this slide before, but let's cover it again. So a byte is a signed integer. And I'll steal this. A short is a signed integer. An int is a signed integer. A long is a signed integer. A char is an unsigned integer. A float is a signed decimal. A double is a signed decimal. And a Boolean under the hood is actually implemented as a numeric, but let's just call it true-false, because Java does not let you do math with it. So it basically treats it as just a true-false value. So let's just deal with these guys up here. Oop. I have 4 different things here, all capable of holding signed integers. Why? Why do I need 4 different types that can all hold? Well, first of all, what's a signed integer? Go ahead.
It's an integer where one of the bits is set aside to denote if it's positive or negative.
Okay, fair enough. That's a pretty detailed example of it, but it can hold positive and negative numbers. That's the punchline. Signed numbers, a signed type can hold negative numbers and can hold positive numbers. All right, how it pulls that off is using a signed bit, as you pointed out. It actually goes deeper than that because they store them as what's called 2's complement, which you'll learn about the 325 class. But you're right, there is a signed bit, so that's you do lose precision because of that. We'll see that here in a second. All right, so why do we need to have so many different kinds of variables, so many different variable types that can all hold positive and negative integers? It seems inefficient. It seems stupid. Now we're back to this idea of right tool for the job. Looks like I have 4 hammers. You know what? All that's different between them is they have different handles. They're all the same hammer. Which hammer do I use? Does it make any sense to own 4 identical hammers? Unless you just have kind of a, emotional connection to these hammers. This was my grandfather's hammer. He built this log cabin with his bare hands and this. And he actually this hammer was without his bare hands, and he made the hammer out of scrap wood from from the log cabin. But logically, it would not make sense to have 4 identical hammers. Right? It might make sense to have kind of a small hammer and then a bigger hammer, like for again, we're back to that whole thing. If you're hanging delicate pictures, the little tiny nails, maybe you don't get the sledgehammer out for that. Drywall tends to not be robust enough to handle sledgehammer blows. So you use a little tiny hammer. It's a lot harder to hit you notice that your chances of hitting your hand with that little tiny hammer, it hurts less, but is much higher. So I have my wife do it.
Hold it or
Do the whole thing. I mean, I convinced her because she's the better designer. So I'm like, oh, where should these pictures be, and make sure because if I hung them, it's just they'd be all unlevel and stuff. But then you say it's like, oh, I'm just channeling Picasso. It doesn't have to be. So why do we have 4 different ways of holding positive and negative numbers? Go ahead.
Memory, because each one of them going to take, if you want to save up in your memory instead of, and you know what you're going to use for it.
All right, so these guys aren't quite identical. Right now, as I have it written, they're 4 hammers with different color handles. But the reality is that these are actually different size hammers. Okay? So our byte, this guy, is 8 bits. A short is 16 bits. An int is 32 bits. A long is 64 bits. What's a bit?
0, 1.
A single 0 or a single 1. That's a bit. Okay? So that means to represent a byte, we have 8 bits to work with. Okay? And as he pointed out, one of those bits is going to be reserved for the sign. So for the actual value portion of it, we have 7 bits to work with. So what's the largest value that we can hold inside of a byte? What's the largest number that can be represented with 7 bits? What does 7 bits look like? 7 bits looks like 1, 2, 3, 4, 5, 6, 7. That's the largest 7-bit number in binary. What is that number equal to in decimal? One, 2, 3, 4, 5, 6, 7. Oh, that's not gonna work out that well. All right, so this guy's the 1. This is the 1's place, the 2's place, the 4's, 8's, 16's, 32's, 64. So this is the 64th place. This is the 32's place. This is the 16's place. This is the 8's place, 4's place, 2's place, 1's place. So let's get these guys centered above there. Oop. All right, something like that. So this is base 2. So this position is 2 to the 0th power place. That's a 1. This is 2 to the 1st place. That's the 2's place. 2 to the 2nd power. It's the 4's place. 2 to the 3rd power is the 8th place. 4th power, 16th. 5th power, 32nd. 6th power, 64th. So to get our actual value here, we'll take 64 times 1 plus 32 times 1 plus 16 times 1 plus 8 times 1 plus 4 times 1 plus 2 times 1 plus 1 times 1. So we add all that together, we get 127. That's actually interesting that it popped that up. Oh, it's because I pressed enter and it did the calculator. So that's 127. So the largest number I can represent in a byte is positive 127. Because I only have 7 bits to work with for representing my number. Now, the smallest number is a bunch of zeros, right? Smallest number is a bunch of zeros. So this guy. So that is 0 times 1, 0 times 2, 0 times 4, 0 times 8, blah, 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 which gives you 0. 0 times anything will be 0, so you add up a whole bunch of zeros, you get 0. But wait a minute, we said it's got to hold negative numbers. So he mentioned that we use one of the bits for the sign bit. And then I kind of mentioned it's a little bit more complicated than that. We encode the numbers in what's called 2's complement form. So the reality is there's a 1 out here, and this is actually in the 128th spot. 64 times 2 is 128. So this value in 2's complement form is actually negative 128. Make sense? In here, you won't have to convert negative numbers. That's something we do in 325. But in here, I do expect you to be able to convert values. And we did that in 200, right? Okay, and we'll review that here in a second. But it's you do need to understand what we just did. And also understand that this isn't some special algorithm for binary. Because this works the exact same way if we're dealing with decimal. So if we take the number 236 in decimal, base 10, our number system, the one we're comfortable with. This is the 1's place, that is the 10 to the 0's place. This is the 10's place, the 10 to the 1's place. This is the 100's place, the 10 to the 2's place. So this is 2 times 100 plus 3 times 10 plus 6 times 1. And that equals 236. So we just converted from base 10 to base 10. An exciting waste of time, but you saw it was the exact same algorithm that we used for converting from binary to base 10. In decimal, since this is base 10, this was the 1's place, but we calculated that it was the 1's place because it's 10 to the 0 power. And a number to the 0 power is 1. This guy is the 10's place. The 3 is in the 10's place. That is 10 to the 1st power. Whereas in binary, this guy was in 2 to the 1's place, which is the 2's place instead of the 10's place. This guy was the 4's place. This guy was the 8's place, 16, so on and so forth. So we kept next power. Multiply by 2, multiply by 2, multiply by 2. In base 10, we're multiplying by 10, multiplying by 10, multiplying by 10. We were dealing with base 16, we'd be multiplying by 16, multiplying by 16, multiplying by 16. All right, so converting any number from its current base into base 10, we use this exact same formula. The one little caveat we run into, I think it's 2589 is my favorite number. So let's say this is 2589 in hex. That's base 16. And I want to convert that into base 10. So that's going to be 9 times 1 plus, actually, hold on, I'm lying to you here. I want to do that in hex because I'm going in the other way. So BAD in hex. Because it's base 16, we have to have 16 unique characters to represent. You might say it's 16 unique digits, but it's actually not a digit. Digits base 10, 0 through 9. So these would be hextets. We have 16 unique hextets to represent hexadecimal numbers. So we have 0 through 9, and then A through F. Okay, so an A is actually a 10. This is a 14. This is an 11. That make sense? So this is D times 1. So that's 14 times 1 plus 10 times 16 plus 11 times, what's that, 256? 16 times 16? Yep, 256. $29.90. I think I got this wrong. Is A is 10, B is 11, C is, oh, this is 13. D is 13, not 14. See, they said you got to know your ABCs. 29.89. I had 25.89, but I just had the number wrong in my head. 29.89 is the right number. So that's my favorite hexadecimal number. It's bad because it. So if you go 25.89 or 29.89, convert it from decimal into hex, you get BAD. It's a fun one. Okay, but we use the exact same algorithm here to convert it. We just had to convert our A, B, and D into the equivalent decimal numbers. We had to convert it from the hextets into decimal values for us so we could do the math. Because I guarantee if you try to multiply D times 1, you're going to have problems. We typically don't do math with letters. Okay, so all those conversions are kind of the same. That's going from some base to base 10. We can go the other direction too, but that's not related to what we're doing right now, so we'll introduce that once we get to something that it relates to. So a byte can hold negative 128 to positive 127. A short can hold negative 65,535 to, no, I'm sorry, 32,768 to 32,767. So this is plus or minus 2 to the 15th power. That's how we get in those numbers. Because one of these 16 bits is used for the sign. So if I come in here and I say 2 to the 15th power, we get our 32,768. Throw a negative sign on it, that's our smallest number, negative 32,768. Largest number is one smaller than that because we lost one bit because we were storing it for the negative. So negative 32,768 to positive 32,767. This is negative 2 billion to positive 2 billion. So that's 2 to the 31st power. So there's your 2.14, 2,147,483,648. 2, that's a negative that, to 2,146,483,647. That's the range of values for an int. You don't have to memorize those. It's just the thing. A long is negative big num to positive big num. All right, so it's going to be 2 to the 63rd power, which I'm sure is going to give it to me in scientific notation. So I think that's 9.2 quadrillion. I think that's what that comes out to. Big number, right? Now, is it infinitely big though? So certainly not something that we feel that we're going to have to, that we're going to require very often, right? We every now and then we need the sledgehammer, okay, in real life, but not that often. Every now and then we might need a data type for holding really big numbers. In fact, sometimes you might even, he asked earlier if we have a long in Java. And to be honest, it might work. I have not used it in Java. I suspect it will not work because there are object types called big integers for holding numbers that are larger than a long. So it seemed to be a double, like, why have it when we have an object type? But in older languages like C and C++, you can make like a double long, okay, which would be 128 bits. So you could hold even 2 to the 127th power, which would be an even bigger number. Okay. So in any case, we can say that these 4 signed integer types can probably house most math values we're going to work with. Fair enough? But not necessarily all. So Java does have a backup plan where there is an object type, and we'll talk about object types here pretty soon. But it has a backup plan, an object type that can hold arbitrary size integers at the cost of performance. The bigger the value you try to put in there, the slower it gets because it's having to, and also the more memory it's going to take up because it's not a fixed amount of memory like these are. All right. So 4 different hammers for 4 different size jobs. The reality, though, and this kind of comes into kind of general practice, is most C#, Java, C++, C programmers will use an int all the time. And if they need a bigger value than 2 billion, they'll use a long. In modern programming, you will never see somebody use a short. You would have to look at some fairly old C and C++ code to find somebody using a short. A byte you will still see sometimes, but for a different reason. The reason you'd see it is because if you're doing like streaming video, streaming audio, typically you're working with it in 1 byte chunks. So that just happens to be the right data size for what you're getting. So it has nothing to do with the fact that you care about memory. So now this all goes back, I said these came from the C programming language, which was in roughly 1968. Okay, so before any of you were a thing. Well, before I was a thing. Okay, so why do we need these today? Or why did we need them back then? 1968, why did we need 4 different size hammers? Why didn't we just always use ints? Go ahead.
Because memory was a kind of rare commodity.
Expensive. We didn't have a whole lot of it, and anything you could get your hands on was really expensive. The example I probably used last semester was, in 1996. So much more actually 1995, I think. Much more recent than 1968. I had a computer that came with 8 megabytes of memory. Most of your machines now, if you bought a budget pleaser laptop, probably had 4 gigabytes of memory, right? So 8 megabytes of memory, a lot smaller than 4 gigabytes. And when I doubled the memory on that to 16 megabytes, it cost me $1,000. $1,000 for 8 megabytes of memory. And if you do the math on this, so 8 megabytes. So divided by 1,000, well, here, let's get it. Divided by 1,024, that gets me gigabytes. So that's 0.0078 gigabytes. So if I do 4 divided by that, your budget pleaser laptop today has 512 times more memory in it than my machine had then. Okay. Now, I spent $1,000 to get 8 megabytes. That is after the price of memory had started coming down. That's after it got cheaper. Not as cheap as it is today. Today, you could walk into Best Buy, pay retail for a 4 gigabyte stick, and what is it, $50? Something like that. Not expensive. You want to get it off of Amazon or Newegg or something like that, you're probably going to pay $28 for a 4 gigabyte stick. Cheap. Okay, so by today's pricing, we'll just use the $50 thing. We'll use the retail thing. So we're going to say 4 times 1,024. That gives me megabytes. Divided by. Okay, so now that's megabytes. So I want to take that value, and we said $50. So that's the price per megabyte today in dollars times 8. So I spent $1,000 for something that you can buy for less than a dime today. Nobody's selling an 8 megabyte stick, but if you could buy it in that denomination, it would cost a dime. Price of memory has come down. All right, so we live in a very different world today than we lived in back then. Back then, as you point out, we had a limitation of how much memory we had anyways. We didn't really have the capability of stuffing that much memory into a computer, regardless of how many dollars you were willing to throw at it. And then on top of that, the memory you could get your hands on was really expensive. And if you have something really expensive, you probably want to be a good steward of it, right? You want to take care of that amount of how you use that, because it's a precious, expensive commodity. So back then, as a programmer, if you needed to count between 1 and 10, you were probably going to choose a byte, because that was the best use of the memory that you had, knowing how precious the memory you had was. Today, we don't care, right? It's an int. If that's not big enough, it's a long. If I need something bigger, I don't care. You got 4 gigabytes of RAM. That's a lot of integers. That's a lot of numbers. Who cares? Or one really big number. Yeah. All right, so that's why we have all these different guys. All right. Now, floats and doubles, pretty much the same argument as ints. Okay, these are positive and negative decimal point values. They are a certain size before the decimal point. They're a certain size after the decimal point. So these actually have a larger footprint than ints and floats. But a float is kind of like an int. A double is kind of like a long. Now, what's interesting there, though, is that common practice for modern programmers is to use a double, not a float. So a double is 64 bits before the decimal point and 32 bits after the decimal point. I mean, I'll never quiz you on that. But just kind of understand that that's the point. Doubles are the bigger version of our floating point numbers. But normal programmers today will use ints for all integers unless it's not big enough, and we'll use doubles for all floating point numbers, I guess, unless that's not big enough, and then you have some object types to jump to. All right, so the beginning of next class, we'll briefly talk about the purpose of chars, and then hopefully we can actually jump into Eclipse next class. So what I will ask you to do for Tuesday, I won't assign it, just I'm going to ask everybody to do it. I already have a link up on Blackboard for it, but go to eclipse.org, this website, and download the latest Eclipse. So download the Eclipse IDE. It's called Eclipse Oxygen. So it'll pick for your platform if you're Linux, Mac, Windows, whatever. And then when you go to install it, it'll ask you what you want to install it for. You want Eclipse for Java developers. Okay? Because there's Eclipse for C++, Eclipse for Python, something. You want the Eclipse for Java developers. All right, so get that installed for Tuesday so that you have your environment all set up for our first homework assignment. Sound good? All right, I will see everybody next week.